We mentioned two theorems. The first theorem is the theorem 16.1.8. So this theorem shows that the Lorentz series converges absolutely in the convergent open annulus. So we can find a beta and find an alpha. So the open annulus with inner circle with radius beta and the outer circle with radius 1 over alpha. That in this annulus, the Lorentz series converge absolutely. Now, the next theorem shows that suppose we have a Lorentz series about the point z0, and the convergence open annulus is a z0 beta 1 over alpha. Then the Lorentz series converges uniformly. In the closed annulus A bar z0 1 R2 with whenever beta is less than R1 is less than R2 and less than 1 over alpha. Okay? So this is z0. This is beta 1 over alpha. So we have A z0 beta 1 over alpha. This is the open annulus. And if we form a new closed annulus, so we have this one. So it's closed because it includes the two boundary circles. Okay, so in this closed set, the Lorentz series converge uniformly. Okay, because this is a series of functions, right? It actually each term is a function of z, okay? And so we have a double-sided series, okay? And this double-sided series converge uniformly. Right. So the proof is quite simple. So please, I will give you the lecture notes tonight. So this is quite reasonable. The remark is here that the Lorentz series may not converge uniformly in the open annulus. Even though it converges in each cross annulus in this open annulus, but in terms of the whole open annulus, right, the Lorentz series may not converge uniformly. Okay, not converge uniformly. So, so you have to know that. The next topic is that a complex function f of z defined in an open state, okay, is called representable by Lorentz series omega if to every open annulus A is 0, R1, R2, so R1 can be 0, right? And this then R2 contained in the open state so there correspond, right, to the Lorentz series about the point 0, 0, which converges to fz, okay, in this open annulus. Okay, so suppose that we have an open state, and maybe we have some cut. Okay, so this is our open set here. We have open set, and right now for every open annulus, right, in the open set. So suppose we find an open annulus, could be here. So we find a z0 here. So 0, the center is outside of omega, right? And so we right? So you see that the open annulus, so we see A, Z0, R1, R2 contained in omega, right? So we find we have an open annulus, right? contained in the open set. Then there corresponds a Lorentz series. Okay, so now we can find a Lorentz series about the center Z0. This Lorentz series converge to Fz. Okay, so converge to Fz in this open annulus. Of course, you can find another open annulus, right? For example, here, this is Z0, and this is R2. So this open annulus, right? So the point Z0 is cruded, right? So it's a little circle without the center. Okay, so this one is also contained in open set. And for this open annulus, we can find the Lorentz series. And actually, because actually C0, the f of z, right? F of z is defined because Z0 is also in omega. It turns out that the Lorentz series becomes to the power series. Okay, turns out. So anyway, so this is a kind of extension to our previous result, because in chapter 15, yeah, we said analytic function defined in an open set is representable by power series, right? So we proved that before, and here we have a corresponding theorem. The corresponding theorem is here. It's called Lorentz series representation. Of analytic function. Okay. An analytic function f of z defined in an open state. Okay. Is representable by Lorentz series. Okay, so any analytic function has this property. Okay, so if Fz is analytical in an open set omega, and if we find an open annulus like this one or this one contained, the whole open annulus contained in the open set, you find any such annulus, then you can find a corresponding Lorentz series. Okay, Lorentz series, and this Lorentz series will converge to the same analytic function in the open annulus. For this situation, because that if the analytic function cannot be defined in this whole, okay, then you can concede that this Lorentz series has non-zero coefficient for n which is negative. But in this case, because that this open annulus in here, this one is contained in the disk, right? The disk includes the center, but the open annulus does not include the center. Okay? So this is the proper set of the disk. Now, for this case, the f of z, the analytic function is analytic at the center. So you can consider that the Lorentz series corresponding to this open annulus is indeed a power series. That means that the coefficient Cn is 0 if n is negative. Okay? Right. So the Lorentz series representation, we can regard this theorem as an extension from the power series representation of the analytic function. Okay, so we can deal with a representation by Lorentz series in such an annular, or open annular subset of the open cell. All right. Okay, suppose that okay, suppose we have a situation. We have center z0 and an open annulus. This is R1, R2. Okay, so we have A, Z0, R1, R2. And consider another situation that we have another open annulus. This is Q2. This is Q1. Okay, so we have okay, and here we have A, Q0, Q1, Q2. And these two open angles has now empty intersection. Okay. So the intersection is here. This is the intersection part. Suppose we have an analytic function, okay? And so suppose we have an analytic function has, so here, corresponding to the f of z is written as Okay? And also the same function is represented as okay? And we have say this is our omega open set. Okay, and could be we have a hole, something here. So now, so the situation is just like here, but now we have two open annulus, and they all intersect. So they have intersection here, right? And as the theorem said, okay, for this open annulus, because this open annulus is contained in the open set and also is contained in the open set. Okay? So now we have two. We have two. And by the theorem, for this open annulus, we have a Lorentz series. And this Lorentz series converge, all right, to Fz, because this is the definition of representability, right? So because it's representable. Now, for the yellow open annulus, all right, the analytic function can be represented by another, or another Lorentz series, right? Okay, so we have these two. And because they have overlap, okay, so you can think that actually the conclusion is that the coefficient should be the same. Okay? They should be the same. Because they have, you can think about the intersection. Okay? So the intersection is equal to, Z0, and so it's R1 and the Q2, right? So this is the intersection. Right? And so for this open annulus, they will have okay. And so let me complete the theorem. And the reason is here. The reason is here. So it just say that any analytic function is representable by Lorentz series. So that is so each open annulus A and omega, there correspond, okay, a Lorentz series extension of f of z at z equal to z0. So this extension is here. Okay. And we can compute the coefficient. The coefficient can be evaluated by this formula. Where gamma is any simple closed path in the open areas. Which in circle, right? The inner circle with center is 0 and radius 1, oriented counterclockwise. So the statement of the theorem is up to here, up to there, that for any open annulus in the open set, the open set is the defining set for this analytic function. And so there corresponds the Lorentz series expansion. And the coefficients can be computed in this way. Okay. And gamma is a simple closed path. Okay, a simple closed path. Because the 1D number is 1, right? So it's simple. Otherwise, we have to put one number here. So we use simple closed path in the open annulus. Okay, so now, so the coefficients, the reason why they have the same Lorentz series expansion means that they have the same coefficient is because we can find a simple closed path in this intersection, right? So here, right? So this is our gamma. Okay. So gamma is in here, gamma is also in here, right? So we use the same gamma to compute the coefficient Cn and Cn tilde. And of course they are the same. Of course they are the same. Okay? So the formula, so the theorem, the statement of the theorem answer make sure that our intuition, okay? This is our intuition, right? So we say that this should have the same Lorentz series expansion. And fortunately, we know how to find a formula. We have a formula to compute the coefficient. So this is true. But if we have two open annulus, right? They have no intersection. Then the Lorentz series representation here is more often different from the Lorentz series expansion here. Okay, they will have different. Okay, so this is about Lorentz series representation of analytic function. Okay, so let's take a couple of examples. So do you have any questions about that? Okay. Okay, so we can see the fz equal to 1 over 1 minus z. Okay, so this function, right, is analytical. okay, in the open set. Omega is the whole compass plane except the point z equals 1, right? So this function is analytical except here, 1. Okay, except here. So we have I put a cross here, means that the analytic function fz does not actually defined at this point. Okay. Now, consider an open disk. Alright, so now consider an open disk. So this is open disk. Right? So the open disk, this open disk is contained in the open set. Right? So the whole disk is contained in the open set. Okay, and so in this open disk, this function is representable by a power series, right? From a theorem in chapter 15. Okay, so what is that? Okay, and so now f of z is 1 over 1 minus z. So this is equal to z. Okay, so now for all z in the open disk with the center 0 and radius 1, the analytic function can be represented by this power series. Very simple series, okay? And you can see that alpha is 1, right? Alpha is 1. So the ROC is 1. Is 1. Okay? So we find the power series representation. Right? So we have a power series. If we okay, so we have a power series representation. Now, okay, and consider the open annulus. So this we have 0, 1, and infinity. Okay, so now we can, the center is 0, right? We have open annulus. The inner circle is with radius 1, but the outer circle there is no, is unbounded, okay? So this is included. So this is an open annulus. Okay? Now, in this open annulus, by the theorem, we should have a Lorentz series representation. Okay? So, so how can we do that? Well, the same, 1 over 1 minus z. But we do a little bit trick. Right? So we take a factor z out of the denominator. So we have that. Okay? And so now, by expansion from 1 to infinity minus z minus n. Or you can find it n from minus 1 to infinity minus zn. Either way, okay? You can see. So it consists only what? Only coefficient with index which is negative. Okay. And this one is true for z in the open annulus. Okay? So this is a Lorentz series. See here? This is Lorentz series here. Alright, for the Lorentz series, you can compute alpha, right? Alpha, then so. But for positive n, the coefficient is 0, right? So you have insert 0, that is 0. For beta, the insert goes to minus infinity. No, go to infinity and c minus n. Okay. And c minus n for n go to infinity, it is always equal to minus 1, right? So when you take the f value, it always equal to 1, so it's 1. And so infinity is 1 over 0, okay? Because alpha is 0, right? 1 over 0 is infinity. So for this simple analytic function, it's analytic in this open set omega. The omega is the whole convex plane, excluding the point z equal to 1. Okay? And so, because z is undefined, so we have a disk, the whole disk here, okay, in open set omega. So we have power series representation. But outside, for this open annulus, we have Lorentz series expansion, okay, like this one. Okay, so this is one example, simple example. Let's see a second example. F of z is equal to minus 2z plus 3 divided by z squared minus 3z plus 2. Okay, and you can see we can do the factorization. Okay, so and this function is analytical in an open set. Omega. Omega is the whole convex plane except a finite set 1 and 2, right? So we have 1 and 2 here. So these 2 points. At these 2 points, the function is undefined. Right? And but this function is analytical at other points except this point. So now we will consider one disk and 2 open annulus. So the first one. Okay, this one. This is the disk 0 and 1. Okay. So the whole disk is contained in omega. Alright, so around z equal to 0, we have a power series extension, as we expect. But the second one, the open annulus, from radius 1 to radius 2, here we have open annulus. It's also contained in that. And we have another open annulus. A, 0, 2, infinity, also contained omega. Okay? So we expect for the yellow open annulus, we have a Lorentz series expansion. Okay? And in the red open annulus, we have another Lorentz series expansion. And these two Lorentz series expansions should considerably they are different because they have no overlap. Okay? So let's see how to get those to Lorentz series expansion and also this power series expansion. Alright, so the technique is here by using partial fraction. We deliberately write in this way. Right, so it can be decomposed to two terms. Okay, so this function is the sum of these two terms. Alright, so now we first expand the first term. We have experience here. so we have that 1 over 1 minus z, okay, and from 0 to infinity is z to the nth power for all z in the disk. Alright, so no problem. The other way is that we have experience. So it's from minus z to the minus nth power for all z in the annulus 1 and infinity. Okay, so we have that. Okay, so in this open annulus, this Lorentz series converges to this function. Okay, so we have this pair. How about the other pair? Okay. Well, the other pair we can see this is 2, 1 minus z over 2. Okay, so pretty much like this one. We find this is equal to 1 over 2n plus 1 zn. Okay, and so this is the power series. So this is true for all t in the open disk. True. Okay, for all z. So for this one, for this particular function, right? Because this function is undefined at z equal to 2, right? But it is defined at z equal to 1. Do you want to see here? Right. And the other way is that minus 1 z 1 minus 2 over z, and we find that this is n equal to 1 to infinity minus 2 to the n minus 1. 2 to the n minus 1 is very big. As n go up, this is exponential function. And for all z in the open annulus, 2 to infinity. Okay, so now, so we have to okay, now in this open disk, right, is open disk, this function has power series expansion. This function also has power series expansion, right? Because it's bigger, right? So in this open disk with radius 1, that this both function has power series expansion. So we see that so L of z Okay? So it's the sum. It's 1 plus okay, so now in this open disk, we find the power series expansion. Okay, now in the open annulus, for the open annulus here, the yellow region, in the arrow region, this function has power series expansion. It's this part. Okay, but this function has the range series expansion already here. Okay, because the yellow open annulus is a subset of this open annulus. Okay, so we find n from 0 to infinity, 1 over 2n plus 1. N plus n from 1 to infinity minus z minus n. Okay, so this is the yellow part. How about the red part? In the red part, in the red annulus, both series has a range series expansion here. This one and this one here. So we have summation from 1 to infinity minus 1 plus 2 to the minus 1 z minus n. Okay, so we have that. Right? So we have 1 power series expansion and 2 Lorentz series expansion. Okay. Any questions? Okay, the section, second section is about singularities and zeros. A complex function f of z is said to be singular. Okay. Or to have a singularity. Okay, at a point z equal to z sub 0. If f of z is not analytical, perhaps not even defined. At z equal to z 0. For example, this function, okay, is singular at z equal to 1, okay, because it is not defined. at this point. Also, the same function is singular at z equal to 2. Okay, so it has two singularities. Okay, so this function has two singularities. But, so they have, but every neighborhood of Z0 contains points, okay, at which f of z is analytic. A little bit complicated here. So it says that we have the function has a singularity at the point z equal to 0. You have two conditions to be met. One is that at z0 the function is not analytic, or perhaps not even defined there. The second condition is that in every neighborhood of z0, right, there exists at least one point in the neighborhood. The function is analytic. Okay? A single point z0 of a function fz is called isolated if fz is analytical, okay, in a neighborhood of z0 except at a point Right, so for this function, this function is analytical at every point except 1 and 2, right? So, for any neighborhood, for every neighborhood of 1, you see that the whole neighborhood, point in this neighborhood, the function is analytical, but the function is not analytic at the center. So 1 is an isolated, because it has been isolated by this neighborhood, right? And also 2 is also an isolated single point for this function. Example, which single point is non-isolated? Okay, consider tangent of 1 over z, this complex function. This complex function has a non-isolated single point, singularity, right, at z equals to 0. Of course, at z equals to 0 is undefined. So of course it's undefined, so z equals to 0 is a single point, of course. But it's not isolated. Why? Not isolated. Why? Because at z0, no matter how small you have, okay, no matter how small you have, you can always find, okay, you can always find a point, a real, this point is a real number, which is 1 over, say, 1 over 2n plus 1 pi divided by 2. Okay? So And because n can be for all n, okay? Because tangent 1 over 2n plus 1 pi divided by 2, okay, is equal to and 1, right? Inverse. This is tangent 2n plus 1 pi divided by 2. And this is what? This is infinity, right? So it's a singularity. So you have a lot of singularity here. And also here. You have a lot of singularity. So it's not isolated, because when we say isolated, it means that we can find a neighborhood. And in this neighborhood, at every point, the function is analytical, except the center. But for here, no matter how small of the neighborhood, you can always find a point other than the center, such that the function is singular. All right. So this point is non-isolated singularity. Okay. So singularity has two kinds: isolated singularity, non-isolated singularity. Okay. So we have two kinds. I will study single isolated singularity. Basically, okay, and because it's very common to encounter in complex analysis. So if Z0 is an isolated single point, of a complex function f of z defined in an open set omega. Then, by theorem 16.1.1, f of z is representable by a Lorentz series expansion. Okay? And this Lorentz is in a punctured open disk B prime the punctured open disk, okay, D prime is actually it's an open annulus. The inner radius is 0, and the outer radius is R. Okay? And 10. Alright? Because the analytic function, right, is analytic at every point in the neighborhood except the center. Okay? So the Lorentz series expansion here, so we can select a punctured open disk. An open means that this kind of open annulus. Right. And from here, because this is beta, right? And this is 1 over r. This is beta. Okay. So it implies that, so it is clear that the beta is equal to lim su. N goes to infinity. and c minus n, okay, is equal to 0. So beta should be 0. So you can see the coefficients with negative index, the lim suit is equal to 0 if we have an isolated singularity. Okay, this is consequences. Right, so this is very important, you know. Okay, and we know, of course, we know that this is less than or equal to. So this implies, because this is 0, this implies that beta is the limit and goes to infinity. This is 0. So actually, the negative coefficient, all right, take the x value and check the nth root as the limit, which limit is equal to 0. Now, the negative power series, okay, summation n from 1 to infinity, c minus n, z minus z0, nth power. So this is the negative power series. Okay, so this is part of this orange series. This negative series is called the principal part. Okay, the principal part of f of z at the isolated singular point z equal to 0. Okay, so this is called the principal part. We will refer to that. So for any isolated singularity, you will always have a non-zero principal part. Okay, a non-zero principal parts. Okay. Now, if the principal part, okay, so if the principal part has only finitely many terms, okay, so it means that n1 to infinity okay, with c minus m not equal to 0, but c minus n equals 0 for all n greater than m. So it means that the principal part has only finite many terms. Okay? If this is the case, then the singular point is called a pole. Then Z0 is called a pole, right? Of order n, because it's the minus n. The minus n is non-zero, right? So it's a pole. A pole of the first order is called a simple pole. Okay. Finally, and if the principal part okay, has infinitely many terms. Okay? Then this function of z is said to have at z equal to z0 an isolated essential singularity. Okay. So isolated singularity will be divided into two categories. One is called pole. The other is called isolated essential singularity. Okay. For poles, its principal part has only finite many terms. If the principal part has infinite many terms, then the singularity is called isolated essential singularity. And the behavior of the function fz at the pole and the behavior of a function at an isolated essential singularity are very different. They are very, very different. Okay, and so we will see some of the behavior on Thursday. Okay, on Thursday. Okay. Any questions? All right. So see you on Thursday.